Hi everybody. In this video, we are going to talk about the application of limit theory in deriving some derivatives, which are famous functions. And we are going to derive some famous functions that derivatives formulas that you used at school and you also use in university level. So which are they? I have written here some set of these mostly used ones, but the other ones can also be derived using this formula or these methods here. So let's start from the first one. The first one you see here, the derivative of x to power n. It's the power function. We know that the power function we get derivative n times x to the power n minus 1. So we are going to today to try to prove it. So first, let's try to give the definition of derivative. We know that the derivative of the function at any point is such a limit f tends to 0. So fx plus h minus fx divided by h. So this is a formula which we use for a general definition of the derivative. So here you can see that if this limit exists, then the function has got the derivative. So we are going to apply the same thing here. So if y equals to x to power n, then we have the following. So fx equals to x to power n, fx plus h equals to x plus h to power n. So substituting everything here in this limit, we are going to get limit h tends to 0. So fx plus h, it's actually x plus h to power n minus fx is x to power n divided by h. So what we can have here, obviously, if we expand these brackets as the difference of 2 n powers n, so we are going to get something like this: x plus h minus x times. So we are going to get x plus h to power n minus 1 plus x plus h to power n minus 2 times x. And we go like this until the nth term, which is x plus, which is going to be obviously x to power n minus 1. So divided by h. You can see that x and x we cancel here. Remaining h times, we cancel h here, so we can cancel here. So obviously what we have, when we place here instead of h zeros, we are going to get x to power n minus 1 plus x to power n minus 2 times x, which makes it x to power n minus 1 again, plus so on, plus x to power n minus 1. And how many of these terms we have here? We are going to have here n terms, so it's going to be n times x to power n minus 1. And this serves as a proof why the derivative of function x to power n is n times x to power n minus 1. In this video, we are going to touch the root or under root function y equals under root of x. The derivative is equal 1 out of 2 times under root of x when x positive. So let's again use our formula. Y derivative is equal limit h tends to 0. So again fx plus h, which makes it under root x plus h minus fx, which is under root of x divided by h. So we know in such expressions we usually multiply. To solve it, we usually multiply by adjoint expression, which will be x plus h under root x plus h plus under root of x. So we multiply numerator and denominator at the same time. That's what we have to do. So we know here we get limit h tends to 0. Here you can see it's a minus b, a plus b, and we get rid of the uh, roots here, obviously. So what we have x plus h minus x divided by h time under root x plus h plus under root x. So this is equals x's are cancelled, h's are cancelled, so we have limit h tends to 0. We have 1 divided by under root x plus h plus under root of x. So when you place h0 here, you're going to get 1 out of under root x plus under root x. It's going to be 1 out of 2 under root of x. So this is the proof of this formula that we use at school. Another one, very famous one, is the derivative of ln x, natural logarithm function, which is 1 out of x for x positive numbers. So let's try to find its derivative. So y derivative is equal, again, limit h tends to 0. So in our formula we are going to have fx plus h again, minus fx divided by h. In the given function fx equals to ln x, fx plus h equals to ln x plus h. So that's what we are going to place here instead of the functions here. H tends to 0. So fx plus h is ln natural logarithm x plus h minus natural logarithm x divided by h. So we are going to apply here the properties of logarithm function. You know, if h tends to 0 here, we are going to get ln x minus ln x, 0 divided by 0. So it's undetermined form. But how we can solve it? Let's act like this ln natural logarithm x plus h divided by h. So I apply the difference of logarithm function. So it's equal limit h tends to 0. So you can write here natural logarithm 1 plus h over x divided by h. So we can rewrite it like this, limit h tends to 0. So this 1 out of h, which is in front of ln, we can write like this, 1 out of h times natural logarithm 1 plus h divided by x. And it is limit h tends to 0, natural logarithm 1 plus h out of x to power 1 out of x, 1 out of h, sorry. So obviously, if you look at tensor, you can see there is a limit x tends to 0. If you remember, we have such a limit which we call actually we call it the second wonderful limit. So if h tends to 0, we are going to get here to simplify. So it's going to be h out of x. So we have to find here x out of h, but we multiply by obviously by 1 out of x. So this expression, according to this limit, gives us e. So it's going to be limit h tends to 0, natural logarithm e to power 1 out of x. So we know it's going to be 1 out of x. So again, we prove this formula again. Let's continue with the another one. We always say that the derivative of function, exponential function, is itself. So its derivative is equal to itself. So let's see why. So limit h tends to, again, let's write here the formula, h tends to 0. So exponential x plus h, this is fx plus h minus exponential x. This is fx divided by h. Obviously, we can factor out e to power x from both of them. So it's going to be e to power x. We are going to have such a formula, e to power h minus 1 divided by h. So let's deal, this is the factor here which does not concern h, so we can factor it out. E to power x times limit h tends to 0, e to power h minus 1 divided by h. So obviously here we can see that we have the function, the limit of the function, which we have to find separately. Let's find this limit separately here. So I'm going to write on here. So limit h tends to 0, e to power h minus 1 divided by h. So how I can solve it? Let's do here um, some type of substitution. For example, we can write e to power h minus 1, we can take as t. So we substitute as t. So in this case, a to power exponential power h minus 1 equals to t. So equals to t plus 1. So h equals to natural logarithm t plus 1. So when h tends to 0, obviously we get t instead of h if we write 0. So e to power 0 minus 1. So it's going to be e to power 0 minus 1. It's going to be 0 also, you can see. So t tends to 0 also. So I'm going to write my new variable here. T tends to 0. And we are going to get t over. So instead of this expression, I write here t over h, which is natural logarithm t plus 1. So I can rewrite, do here some simplifications for the useful solution. So 1 out of, I can write it like this, 1 out of t, natural logarithm t plus 1. So it's going to be limit t tends to 0. Again, 1 out of natural logarithm 1 plus t to power 1 out of t. So this limit gives us e number e. Again, coming back to the second wonderful limit, we know that this limit is going to be e. So actually what we have here, we have limit t tends to 0, 1 out of ln e, ln e. Natural logarithm is e of e is 1, so we can write here 1. So 1 out of 1 is 1. So placing this value here instead of the limit, then we are going to get if we continue, we are going to get exponential x times 1, which is exponential x. So we proved that again, that derivative of exponential x is equal to itself, exponential x. Now let's do to the last one, which is also widely used, y trigonometrical function sine x. So again, fx is sine x here, and fx plus h is sine x plus h. So the rest of the things is to place everything here. Limit h tends to 0. Sine x plus h minus sine x divided by h. So we can do the formula. We can apply here the formula for difference of sines here. Let me write this formula. So we know that sine alpha minus sine beta is equal to cosine alpha plus beta divided by 2. There is a formula which you know from school, and sine alpha minus beta divided by 2. So we are going to apply this formula here. So our alpha is x plus h, and our beta is x. So it's going to be something like this: 2 cosine. x plus h minus x divided by 2. So obviously it is h divided by 2 times x plus h plus x. You can see here, for h, for cosine, we get plus here. Let me correct it. So, but again, x plus h plus x. So it's going to be 2x plus h divided by 2. Yeah, times sine. Sine, we do the difference, x plus h minus x. So x's are cancelled, sine h over 2 divided by h. I hope this time I wrote correctly. So it's going to be, you see, the idea here is that cosine doesn't make you any problem. So you can anytime write here, instead of h, you write here 0. So we can rewrite it like this: limit h tends to 0. This cosine I am going to separate from the general formula, divided by 2 times sine h divided by 2 h divided by 2. So these two I'm going to put like h divided by 2 here. I have a right to do this, so there is no problem. So actually look here. Here I am going to apply this formula. Limit x tends to 0, sine x divided by x. We know the first wonderful limit is equal to 1. So this limit is 1 actually. So what we have here, instead of h, we place here 0. So we are going to get cosine 2x divided by 2 times 1. It's cosine x. So again, we prove that the derivative of cosine function is cosine function. With this way, again, as I talked before, we can prove all types of derivatives. So all of them come from the definition of the derivative. So you again see what the importance of the derivative is. So different definitions are important to know. They give the answers to the questions why and how we get it. So I hope this video was useful to you. You can analyze these explanations. If you have a question, do not forget to write in the comment section or to directly address to me. I hope to meet in the next videos. Good luck to you. See you. Bye. Take care.